So I'm going to work a couple sample problems so you can go over them and figure out if you know how to do it. You might want to stop the tape after I initiate it and try it yourself before looking at the solution, but that's really up to you. So let's say I have a negative charge, and I want to look at a point that is 2 meters away. So I have a charge, a point 2 meters away, and my charge has to have some sort of value, so let's call it negative 3 coulombs. Negative, of course, because it's negative. So 2 meters away, negative 3 coulombs, my constant is 9 times 10 to the 9th Newton meters squared per coulomb squared. And my question is, what's the electric field at that point? And to solve this, I'd like to bring in my guest solver, Hayden.
All right, so if you want to try this yourself, now would be the time to pause. And if you're looking for the solution, here we go. So we know that the electric field at any point is equal to K Q over R squared. So we're given both a distance, the charge, and of course the constant. So from there we can just plug it straight in and figure out what this electric field at that point is. So from there we get, that's what the electric field would be at that point.
Nice job, Hayden. I'm going to give him a hand. So now let me give you another problem, this one from the next chapter. Let's say I have a positive charge here, and I have a point, again, I'm going to put this point 2 meters away. I'll give it this time a positive 3 coulomb charge. Now, looking at this point, same distance away, what is the potential at that point? Hayden.
So again, now would be the time to pause if you want to try this yourself. So if not, here's the solution. So we know that the electric potential is equal to the voltage at one point, and we also know that the voltage is equal to K times the charge over a distance. And again, Mr. Nickerson has given us all these wonderful components so we can solve for V. 9 times. And now we get 4.5 times 10 to the 9th Newton meter per coulomb. Meter per coulomb, which is positive. So in this case, at the point, there is a potential.
And of course, on that answer there, Newton meters per coulomb are actually volts. So I've drawn here a sort of third scenario that we can go over, and that is if we have two long parallel plates with a lot of negative charge on one side and positive charge on the other. If there's an electric field of 10 newtons per coulomb between these plates, and I put a charge in of 2 coulombs, my question is, what is the force on that charge?
So now is the time to pause the video and try it yourself, or if you're ready to see the solution, keep on watching. So when there's ever a positively charged plate and a negatively charged plate, a uniform electric field is generated. And based on the definition of that field, we know that the field is equal to the force divided by the charge. And if we manipulate this, we can directly solve for the force in a charged particle inside a field. And we get that the force is equal to the electric field times the charge of the particle. And luckily, Mr. Nickerson gave us both of those things. So we just plug it into the equation, 10 Newton coulombs, or 10 newtons per coulomb times the charge of the particle, which was 2 coulombs, and get a force of 20 newtons. And in order to find which direction we just applied, kind of some simple electromagnetism logic, where we know that the charge, 2 particles of the same charge, positive and positive, repel each other, while objects with oppositely charged particle with opposite charges attract each other. So the protons, or the positively charged particles, is going to be attracted to the negative plate with a force of 20 newtons.
Thanks, Hayden. And for any more problems, you can go and check out the quiz, and the answers are on there. Thanks.